So let's take a little example of radioactivity, a radioactive decay, and showing why that can happen. So, in terms of what is going on, in terms of why things happen as a kind of energy perspective. Okay, and the key thing here to remember is that when you've met this equation, delta E equals delta mc squared, you get a change in energy due to a change in mass. And what you hopefully remember from when we did, when you covered nuclear fusion in the sun, is that that could happen because if you had 410 hydrogen protons, and you had them together, they would have a certain mass, and you combine them to make a 4-2 helium nucleus. There was a loss of mass in doing this. Okay, so this combination has less mass than this combination. So the loss in mass means energy is given off, and that loss in mass occurs because we'll talk about the balance with strong nuclear force. You're doing work being either done by or against a strong nuclear force, which leads to this sort of result. So let's deal with just an example of this change in mass of things. Okay, so let's deal with one of the most common sort of isotopes. That's an alpha emitter. So uranium 238 is an isotope of uranium, obviously, that decays via alpha emission to thorium 234. Okay, and so what we have is an example of what we've got: uranium 23892 goes to thorium 23490. So we have a loss of 2 there, plus alpha 42. And what we can do is we look up, or you get told, okay, what is the isotopic mass of these things? Okay, it's obviously very close to the relative atomic mass, but it's ever so slightly different if you actually so the isotopic mass of this is 238.0508 U. It will decay into thorium 234, which has a atomic mass unit of thorium 234. Let's find that one. Thorium 234 is 234.0436. Okay, and then we want an alpha particle, so helium is 4.0026 U. Okay, so we've got this, and we can say, okay, well, what's the mass on this side of the equation? So we've got 234.0436 plus 4.0026, and we get 238.0462. That's a 2. And obviously we've got 238.0508. So there's been a loss in mass of, we take this away from this, we get a loss in mass. So we get 238.0. We have a difference, a change in mass is equal to 4.6 times 10 to the minus 3 U. So that is from every single reaction. Every time this happens, there's a loss in mass of 4.6 times 10 to the minus 3 U. The atomic mass unit has a mass, so 1 U is equal to no, hang on, typed it in wrong, I just lost it. Is 1.6605, so it's 1.661 times 10 to the minus 27. So we can combine that together. So the change in mass is this times this. So times 1.661 to the minus 27, and then we get 7.641 times 10 to the minus 30 kilograms. So that's the change in mass. So therefore, the change in energy is equal to delta mc squared. C is 3 times 10 to the 8, so we would do multiplied by 60, and we get a energy of 6.877 times 10 to the minus 13 joules. So that's how much energy is coming out of every sort of like decay. Okay. Now we can do this and say, well, okay, if we want to kind of get an idea of just how much energy is in this, let's imagine we had just 1 mole. So let's say we had 238 grams of uranium-238. Okay. So we could actually sit there and go, well, how much energy in 1 mole? And 1 mole is 6.02 times 10 to the 23 particles. Well, this might be a small number, but this is a huge number. So if we multiply those two things together, we would get the change in energy from 1 mole of uranium-238 turning into thorium. We would get, so multiply that by 6.02 E23, we get 4.14 times 10 to the 11 joules per mole. This is huge. Okay, so this is a huge amount of energy. Now, just as a sort of thought exercise, we can say, well, why don't we use this as a kind of a power? Why can't I just throw one of them into my house, somehow get the energy from this alpha decay and get energy from that? Well, the reason is that although this is a large amount of energy, it's being emitted over a very long period of time. And hopefully you might remember the concept of half-life. So if you recall that, and we will cover this, that a half-life is the time taken for half of the decays to occur. We can actually sit there and say, okay, so what, how long is a half-life? Well, I can look up the half-life of uranium 238, and I get a variable length. So the half-life of uranium 238, well, that is equal to about 4.5 billion years, which is a long time. So we could then say, oh, in seconds, we would then say, okay, so that is equal to multiply that by 3.15 times 10 to the 7 seconds in a year. And what you get, okay, so we've got to do 4.5 times 10 to the 9 times 3.15 times 10 to the 7. Oh, and we're going to get 4.5 into the 9 times 3.15 7. And we get that is equal to 1.42 times 10 to the 17 seconds. It's about the same age as the Earth. Fantastic news. So if we were to sit there and go like, so, that's one half-life. In one half-life, we would have emitted half of this energy. Okay, so let's say we've got this thing, and we've let over one half-life, we will lose half of it. We lose about 2.07 times 10 to the 11 joules. And it'll take this long. So this says in one half-life, we would emit, I say we're a lump of uranium. So 2.07, so it's half of this number at the top. 2.07 times 10 to the 11 joules in 1.42 times 10 to the 17 seconds. So therefore we have an average power. So how much energy per second? Well, we've got a big number, but it's divided by an even bigger number. So we've got 2.07 times 10 to the 11 over 1.42 times 10 to the 17. And 7, 11 over 1.42. And we end up with, oh look, we end up with 1.46 times 10 to the minus 6. So about 1.5 micro watts. So on a sort of like scale of us, alpha decay isn't a useful power source. Like it's not. But on a particle scale, these are big energies. So for an individual like particle, this is a lot of energy. It's a lot of energy from an alpha decay. It's a lot of energy for your DNA somehow to deal with. No way it can deal with it. But like it's not useful as a power source. And so this is just kind of just taking you through a weird exercise. But the fact that this can happen, the fact we're getting energy out, the key thing really is the fact that we're getting this energy out of each decay. That's why it can happen. If you did this and you weighed up your products and compared them to your your starting thing, if this had a smaller mass, well, you don't get the decay. So it's got to be about going through that decay and getting energy out. And we can do that for a beta. We can also do it, we can do it for a beta decay. Similar thing, we could work through it and say, oh, okay, how much energy would we get out of a beta decay? And maybe I'll leave that as an exercise for you guys if I throw that thing together. There we go.